Hi everyone, this is just a quick little video to show you how to use the scan keyword to measure the potential energy surface of a diatomic molecule. So in the lab manual under exercise D, we ask you to measure the potential energy surface of the I2 molecule to see whether or not it actually resembles a Morse potential. I'm not going to show you how to do the I2 molecule. Instead, we'll start with bromine. It's very similar, and if you just change the bromine to iodine atoms, I think you'll get a very good result. Okay, so to start with, you're going to need to measure an optimum and frequency calculation for I2 to determine the optimal bond length and the energy. We've already done this exercise for some of the other molecules that we've looked at, so I'm not going to go into detail on that. Instead, I'm going to jump straight to the scan keyword. What the scan keyword does is it moves a coordinate, whether it's a bond length or an angle or a dihedral angle, in fixed intervals uh, in multiple separate calculations. This allows you to determine, for example, what the electronic energy is as a function of nuclear coordinates as you break or compress a chemical bond. So to start, we're going to create a new molecule, and our molecule is going to be bromine. So I'm going to select the atoms that I want, bromine, we get bromic acid, add another bromine there to make Br2. So I'm going to go to calculation and setup, and under job type, instead of energy, optimization, frequency, I'm going to click on scan, which will put the scan keyword into our routing section of the input file, and I'm going to click rigid. We don't have any other things to relax as we change these bond lengths, so this is fine. And immediately you see this red line comes up at the bottom of the Gaussian input section where it says the scan coordinate must be added manually in the input file. And if we try and hit submit, we'll get an error and it won't actually let us submit the calculation to Gaussian. Okay, so we need to add this manually. So if we click edit and hit OK, save this, we'll save it as BR2. It will pop up in WordPad or Notepad with the input file. And to know what we need to add, let's take a look at the directions here. So if we go and read the go to the link that's listed in the lab manual file, we'll get to the scan keyword description under Gaussian 09, and you can see that there's a formula for how this is done. If you have a specific variable that you want to scan, in our case it's going to be the bond length between the two bromine atoms. You have the variable name for the variable name that you want to be moving, a starting point, the number of positions that you want to measure the electronic energy at, and then what increment do you want to move it by. So in the lab manual, we tell you to look at a bond length that ranges between 1 angstrom and 7 angstroms. So to do that, I'm going to go to this to the input file that popped up, and currently it says B1 is 2.28 angstroms. That's the bond length between this bromine atom and the first bromine atom. I'm going to change that, start at 1. We'll give it 70 increments in 0.1 angstrom increments. Now all I have to do is save this file, close it. Gaussian will automatically ask if I want to submit the file to Gaussian. We'll say yes. This this calculation will take a little bit longer than previous calculations because in effect it's calculating 70 different electronic structures. Okay. So while this goes, we'll just wait for a minute or two and see what happens. Whew! Alright, it finished. The Gaussian job is completed. Would we like to open the Gaussian window? Absolutely. Again, we're going to open the log file, not the check file. And we see that it starts out in the compressed format the results file shows us the starting point. And now, if you look in the upper left-hand window of Gauss View, we have this frames. If we increase this, you'll see that it's increasing the bond length. And now we see that we've broken our bond, and these bromines are no longer forming a strong covalent bond. We can go further and further out, and we can look in the results section and see what the energy is as a function of each position. Luckily, Gauss View has a quicker way for us to get at this information. If we go to the results, we see that the scan keyword is now available, the scan results. And we can see a nice plot of the total energy as a function of the scan coordinate. We can zoom in and look at the interesting points. The circle in red highlights which frame we're currently on. So as I decrease this and bring the atoms closer together, you see that this point moves closer in on the curve. Now, this is fine. This isn't a great plot, and this isn't a plot that I would want you to put in your lab reporter in the DFT worksheet. So instead, we're going to save the data as a text file to scan. Now, when we go and open this, it's in a format that we can directly open in Microsoft Excel. So if we go to Excel, blank workbook, data, from text file, we go to the desktop, we select our data, we're going to pick that it's delimited by space, finish, import it, and here we have bond length. This is our x coordinate, and our energy y. Now, this is actually still not ideal, and the reason is that these energies are very large, and we want to look at a very small change in energy, right? If you go back and look at this, if you go back and look at the graph, we want to look at a small number of Hartree changes, and our y-axis is huge. Instead, what we can do is we can redefine our energy level by subtracting this level over here. This will create a nice energy plot where the zero energy will be the dissociation energy, and we'll be able to reference the bottom of our well with respect to that energy. I suggest you try doing that when you report your data in the DFT worksheet. I hope these two videos have helped you get a better idea of how to do the calculations for the DFT worksheet. If you have any further questions, please don't hesitate to contact me via email, come to the office hours of myself or the TAs, or pull me aside during the lab class. I'd be happy to discuss this further with you at any point.